Hello there! I wanted to make a new video with just updates of what I have been up to in my hobby of upscaling model training. Something I did is, on my GitHub page I have a lot of releases or frequent releases of models, and so this can change. For example, I released datasets here. In August I released trained models like the HQ series, which is simply trained on good quality non-degraded inputs. You can see examples here. But something I did because I often add new models and because there's a lot of single models to download, because maybe someone wants all the models in here. That's something I used when I have like an input image and I just run it with chainer in a chain through all my models and then see, or even other models as well, and then see which one I like best at the end when looking at the results. What I did in the past is I had, just put all my models into a folder, then archived it with zip or something, but then and then wanted to put it on here, but GitHub file size is 2 gigabytes, so I split it in parts and then I uploaded it here. But it was very suboptimal because if I wanted to update it with new models, I put the new models into the folder and repackaged, re-archived it into, different parts of zip files again, and then replacing all the zip files on here. GitHub also had problems with uploading zip files or 7-zip, super slow, extremely slow, so I changed to tar archive. But very suboptimal, right? Somebody wanted to update all the models, he needed to re-download all those archive parts and then extract them again. This is why it was suggested that I, do archives per month. So, August, and then when August finish, I put all the models in there, and then upload that archive, and then it stays untouched. But what I came up with is a Python script. So if you click on here, there is a Python script you can download down here, and then you can simply run it. I mean, it's shown in here. You give it the Python script and the model folder, and then you can choose, do you want the PyTorch files, which is the most complete, and then it synchronizes that folder. So it looks like which models are already from me in that folder, which ones are not, and then it downloads only the missing models. And the script updates itself. So at the beginning, it gets the newest version of itself. So that makes it way simpler. You don't need to look at GitHub page and see was there a change or not. You can just run the script, puts all the newest models into your folder, done. Then something else I wanted to show, this model. I think it's pretty cool. Or just another something I wanted to test out. This is Age of Mythology Retold released, and I was playing it and I thought it was pretty cool. I liked the old one too, just casual gamer though. But I thought, why do I not combine two hobbies and I make a game texture upscaling model trained on and for Age of Mythology Retold textures, but probably also works on other game textures. And so what I did here, as you can see, I extracted all the textures, converted them to PNG, tiled them all into a tiled sets, then I applied quantization and things and trained a model, which then improved when I added BC1 compression, which Kim suggested, and I used NV-compress for that. And then I used IQR scoring to find the best checkpoint, and then I released the model here. And you can see here Achilles, for example, or then the armor, or then the tiles. Those are just the examples, but now I have a 2x upscaling model for game textures trained on Age of Mythology Retold and on MoSR. 2x, why 2x? Because I thought if it's used for something like that, the biggest tiles I had, the biggest texture files, sorry, were like 4096 by 4096, so pretty big already. And so I thought, well, 4x sounds kind of like overkill, let's do 2x. And then I actually wanted to try it out, why not? I upscaled all the textures, the Greek textures, used the ONNX model, because Chainer wouldn't support MoSR yet. If you're interested, Chainer, you can simply see it here. This is this tool to upscale models where you can make a chain and then simply upscale images or a folder of images or then an image with a folder of different models. And I show it, they extracted the upscaling model out of it because chainer is for a lot of things. You can do a lot of things with it, but they made a package out of it called Spandrel, which also ComfUI uses and others. And you can find all the supported architectures here, and some like MoSR have recently been added, and the package has been updated, but Chainer hasn't been updated yet to use this new model. And you can see, so this is why I used my ONNX conversion. Took a little bit, 7 hours for the Greek textures, and then I simply replaced all the texture files in the game with my texture files. And then I made a scenario, but you can see there's artifacts going on here, roof tiles of the town center, probably the normal files who are just 2 times bigger and stuff. Um, uh, wasn't intended for that. So I only replaced the base color files. You can see the artifacts are gone here. But when comparing to the normal default, it doesn't look different. It doesn't look better or something. It's simply because it's a faithful upscale, right? I train faithful upscaling models, and if I do a 2x model and then it gets, downsized to the same size again, then it looks the same. So that doesn't do anything. And just to check, I inverted the colors on this and then I put it into the game again, and then it's like, yeah, it's actually replacing it. So 2x upscaling Edge of Mythology Retold for in the game doesn't make much sense. Also, the texture files are already pretty big for this game, pretty good quality already. But yeah, the model can still be used though. You can still use it on textures to upscale them. It's just something I wanted to show. It was a little experiment of mine. But then let's go back. There was more I wanted to show. Maybe the newest networks or architectures that we're using in the community are real PLKSR, which is a variant of PLKSR. Span Plus is also a variant of Span, and then MoSR is also is made by UMZI. Those are kind of the newest ones that are community influenced, so to say, or made. And I trained some of them. Well, I tried real PLKSR, multiple models, and then I made a MoSR pre-10 as well, and I made a MoSR model or two. Real PLKSR die sample is also pretty good. What is that die sample thing? It's simply an option when training. A different upsampler than pixel shuffle, because something you can see here, something I want to show, is something I ran into when training real PLKSR or also span and sometimes other things, is this checkerboard pattern. You can see it on the bright colors. This is why I used this image. There's like a grid over it. This is 7,000 iterations with GT size 128. And what is that GT size and what is patch size? So what we had in the past or before was you would say GT size or put it in the config, but then it depends on your scale. So if somebody did a 4x model, then the effective patch size is 32. If somebody did a 2x model, then the effective patch size was 64, and a 1x model, then it's 128. And so that was a little bit confusing, because if somebody says, yeah, I used GT size something in my training, then we need to scale, because otherwise that number doesn't tell me anything. And also, if you said you use the same config for a 4x and the 1x model, you would suddenly run out of VRAM real fast with the 1x model. So we changed that to patch. So now if we say, patch 32, it is patch 32. It doesn't matter on the scale. It's just patch 32. That's the patch it takes to train. Patch size. But yeah, so back to this. So there was this checkerboard pattern, and then we found out that if we increase the GT size to 512, right? So that's 128. Let me see. Yes, patch 128. then you can see this pattern is gone. This is still only 7,000 iterations, so it doesn't look that good. But the grid pattern is gone, and that's because PLKSR used kernel 17. So you needed to train with way bigger patches so this artifacting wouldn't appear. And then we used die sample, right? This is let me see. This is die sample, trained longer. Let me see. Yes, this is die sample, and you see also a pre-train, and you see the artifacts. The grid pattern is not there at all. So this can be trained with lower patches, die sample, and the grid pattern not showing up. This is why I use it now with real PLKSR, for example. One downside when NX conversions need to be static, cannot be dynamic. But here is a full model trained now. This is the Nomos 2 real PLKSR die sample model. So you can see there's no checkerboard pattern going on. You can train or try out training, MoSR or real PLKSR with NeoSR or with trainer Redux. Something I also wanted to show real quick. There is an inference benchmark on PyTorch on the trainer Redux repo. So if you're interested, you can check out some of the network architectures, how fast are they in comparison with each other and how much VRAM do they use in comparison for each other. Some like DRCTL will take a lot, or ATD, and some are way smaller and like span and will take only little. um, and yes, something else I saw that's also just because I'm doing news, I thought I put it in here. I saw there was a Flux dev Controlnet upscaler, which can be simply tested out on a space. So I thought I'd simply take this input I just showed for my model. The last model I released, I was training. I was like, well, let's just take this texture and see if it changes it or adds more detail to it or something. And as you can see, the result was not good here on the right side. Then I thought maybe it's the scale, maybe it's not meant for 2x but 4x, so I put 4x and that's what it produced, which would be interesting how that would look like if I would plug it into the game. Then I thought, well, it's probably not meant for game textures but for real life photographs, so I take this input here from my HQ high quality DRCTL model, and then I put it in here, and the result is good. And something that I found interesting, though, if you look on the right side, I made this little thingy. Flux said, windows without blinds can't be, so it put blinds on there on the windows. I hope blinds is the right word for that in English. So you can see here again that that's the output of my 4x upscaling model. That's the output of Flux. So the thing is, I like my model better, but I'm used to training, faithful upscales, and I think that's not where, and Flux is a diffusion model, so it will hallucinate details. So and is less faithful. So I don't think that's the area where those upscaling, diffusion-based upscaling, res shift, and there are a lot of them. That's not where they shine. I think they shine in comparison to faithful upscaling networks. I think they shine because they can hallucinate details is when the input image is already very degraded to a way that the details are actually missing. So a faithful upscaling network cannot restore those details because they are missing. I took an example here because I wanted to show this of my real web photo .2 model, which I thought is already trained pretty well for a faithful upscaling model to handle like compression and whatever green colors going on here. And I think it did a very well job. So these networks can still be used to restore heavily compressed images, but it cannot, imagine details where there are none. And so we can actually, as a test, I plug it in here, and then we upscale it, and we can see, well, it overdid it. It looks a little bit artsy with all those white lines white lines rampage right here in front of the face and on the neck and everywhere. But where those models really shine is right skin texture. It put skin texture on the face. Like the lips look good, the eyes look like eyes. So that I think that's the case where such diffusion models shine. And that's also something I had already shown in another video, in another workflow, where I took, heavy, compressed images or just destroyed images and then upscale it with my faithful model first and then put it through 1x soup here to get a little bit better result. You can see it here, the same model I just showed, which restores not bad. And then with Super, you can see those blob of trees become actual trees, and the grass becomes actual grass, and the cows become actual cows. So it can help in that regard a lot. For example, while still keeping it, I restrained it a lot to keep it rather faithful to my original faithful upscale. Or another example, where the mountains are pretty suffering, and then it turns those clouds a little bit more into clouds, mountains a little bit more into mountains, uh, and things like that. Good. Something what I wanted to show, what the main purpose of this video was my dataset preparation. I thought I'll do another dataset curation of the HQ-50K dataset, which is 50,000 images here from different sections or categories, sections. And something I noticed, and I'm just going to show what I did. And something I noticed that in the alt text of the download links, they were all JPEG, so we need to expect JPEG compression. So I came up with with little steps, and then I downloaded the dataset, could recover like 80% through those download links. Then I tiled them to 512. Why tiling? It's because it speeds up training, because you need to imagine if we set batch 16, then it takes 16 images, loads them in, and then crops a small section out of it for training. So like, for example, a patch of 64 or something. So a small section of the image. And now if all your images are like 8K resolution, it takes those super big image files and then crops like a super small section out of it that it's actually gonna use. So that's yeah, suboptimal. So better is you have smaller images that it loads, so it loads those way faster and crops images out of it. So that's way faster and uses less, memory requirements. And 512 is still good because you can still go up to a patch size of 128, which is important for if you train the smaller networks that don't really take much VRAM, that don't really have much VRAM requirements, so you can up the patch there to get better results. So 512 should be sufficient for that, but while also speeding up training. Then I did tile size filtering. Those tiles, you can see a lot of them, or some of them were smaller than 1 kilobyte, for example, which means they don't have much information in them, probably just a single color or something, so the model can't really learn from that, so those aren't needed. Then I did blockiness filtering. What's that and why did I do it? So there was a paper that came out September, so beginning of this month, which was really interesting. I can recommend it. But they looked at dataset, the influence of the dataset to model training for single image super resolution, which is great because I don't know if I see many papers in that direction. And something that I showed, they added, compression to the DF2K dataset and the LSDIR dataset. As you can see here. Oh, yes, I have the graphs. So you can see here, they add a JPEG compression and then trained models. And here you can see at 75% JPEG quality compression added, it was pretty detrimental for model training. You can see the longer it trains, the worse it gets, which doesn't happen at 85%. You can see it even more so on the LSDIR. You can see how it first goes up, but then it just falls and falls. The longer you train, the worse the model gets. And you can see it especially, of course, with the 50%, it just, crashes, bam. Um, so that's important. We don't want our model to get worse with training time. So we want to make sure to not add 75% JPEG compression to our dataset. That's kind of the problem I have. I want to filter datasets. My goal, what I showed here is, of course, if I add JPEG compression 75%, then it's detrimental to the image training, model training, sorry. But I don't want to add compression to my dataset. I want to score it and then have some cutoff score where I know, well, now my dataset is safe. So what I tried is just, they showed here the F2K and LSDIR and then the blockiness. And, LSDIR at 75 had 57 blockiness, which is closer to the F2K's 85, the 46, than the DF2K's 75, the 83. So it had way higher values, but for LSDIR, this 57 blockiness was pretty detrimental, while for DF2K, the 46 was still safe. So just to be safe, I went with a blockiness score maximum of 25, just to stay on the safe side that it can't be detrimental to the model training. So that's what I did. Maybe I should have it on the slide. Yeah, here. And I can show you the scores. So blockiness score, good score it received are the images like those. You can see, yeah, good images. You can see I left the noisy one in here in the example and the blurry in here in the example. They scored well, because we're scoring for blockiness here and not for noisy or blurry or something. And then the ones that got bad scores, you can see the compression artifact on the branches, sorry, and in the text you can see here all the compression going on. So I used the cutoff score of 25 and removed any tiles that had bigger or are at 25. So then I wanted to use IQA image quality assessment to filter also, which can be done with the PyTorch toolbox. You can see they have full reference methods and non-reference method. The full reference method you've seen probably, for example, PSNR and SSIM, often used in the papers. So you compare an image with its high resolution counterpart, how close they are together. And with the no reference method, that's what I need to use for dataset curation, is simply you look at an image and then you try to score its, quality. So you want to, yes, just score its quality. And then there were benchmarks to this. You can see that cualign scored pretty well in the sense of it rated, images and people also thought those images were perceptually good quality. And what I did is I used all those metrics because I thought after training a model, you have so many saved checkpoints, which one is the best? So I used all of these, 50 or something to score all the, outputs, validation outputs of my model trainings to find the best release checkpoint. So I ran all of them already, and then there were some I liked, like HyperIQA, Topic, NR, Monica, and cualign. And the thing is, they all perform a bit differently concerning if we look how long we need to score those images, those tiles. You can see a test here with V100. If HyperIQA takes this long, then Topic takes like twice as long, and cualign takes way longer. So if that's something of importance, I just wanted to hint at that. So I scored the HQ-50K with HyperIQA. And you see the score, and here are some of the 8 best HyperIQ scored images and the worst ones. And how I had used that in the past is I simply scored the dataset and sorted according to score, and then I looked like, well, what cutoff score can I use so that still like 4,000 images or more are left. Then you can see, for example, the ArtFest dataset, I removed images below 0.46, but for example, for the nature dataset, I removed images that were below 0.7. So it was a relative threshold cutoff score that I used so far. But now I used cualine because it did so good in the benchmark scores. And you can see I went with 4 or above, which is good to excellent quality. So I used that, and here you can see the 8 best tiles scored with cualine 8-bit. Which I really like on the top right corner is that it still scored an image with blurry background bokeh effect. Very good. That's very good because I once had a case, I think, where I scored with Hyper IQA and it, scored sharpness pretty high, and then it removed pretty much a lot of images that had some blurriness, like in the background, and then the trained model would not handle blurry background that well, or would try to sharpen it. Could have also been the training config though, so I'm not too sure. And here are some of the worst scored images by cualine. And then I added complexity filtering and scored and filtered. Why did I do that? It's also in that paper I referenced previously. They showed, if you look at table 6, they used segmentation based filtering though, but they saw that if they only used images from the dataset that had 100 or more segments in it, then the model performed better. And I used the complexity scoring IC 9600, which I thought was pretty simple to run in the same spirit. Here, the most complex images from that scoring and the least complex images, you can see a lot of just color where the model wouldn't learn anything from that, or not much from that. So I think this would replace, my file size filtering at the beginning. And then you can see the cutoff scores here. So based on that, visually, I just decided, I'm going to use a cutoff of 0.4. So anything below goes, or I keep everything at or above 0.4. Then I did some similarity filtering, just trying to find similar duplicates, visual duplicates. And then I simply used Oxy PNG to optimize the files. And then I landed at this HR folder, 8,000 tiles of those, initially 40,000 or something. You can see here there's still image 12 and 13, for example, look visually pretty similar. I don't think the upscaling model learns anything more from those two, but at the same time, it doesn't hurt the model. Like you can have visual similar images in there. That's totally fine. So then I thought, well, let's do the same with LSDIR. And so I did this little workflow. I came up from this previous experiment and I simply did IQR filtering, then complexity filtering, and then blockiness. It was very good already. And so I had a curated version of LSDIR, and then I thought, well, let's do the same, with flicker faces and everything, and then put together a big or do all of those big data sets, filter them, and then at the end I have a really good training data set of all those merged curated versions. But then I thought like maybe I should test those things in a better manner, like actually testing and assessing them. So I could so afterwards I'm sure this helps or doesn't help, and maybe I could even write a little something about it, report or something, because I remembered in LSDIR in the paper, for example, they had two different data sets, right? The ImageNet and then the one they made, and then they had like those graphs, and from model training it showed, our data set is better. You can see it here and you can see it here. So I thought I could do something similar. And so I decided to take the F2K. So that's a data set that's often used in the papers. You can see it here and you can see it down here. That's often, they use diff2k, they use the F2K. The F2K is simply diff2k and flickr2k combined. I never see, or I don't think I ever see flickr2k used alone in a paper somewhere, but always as a df2k dataset. And together with that, I use the diff2k validation set, which is also, HRs provided and LRs provided, so that's pretty good. And interesting is also that diff2k is a subset of this dataset, and I think diff2k is of higher quality in general than flickr2k, So I wanted to also use diff2k as a baseline. So if I have a good curation workflow, then it should be able to filter from those combined tiles to tiles that will give the same performance than the diff2k tiles, or maybe better. But it was just a comparison point. Will I be able to filter this one in a way that I get the same good quality from diff2k? So you can see I scored all of them. I scored diff2k, all the tiles for complexity, blockiness, and cualign 8-bit, diff2k as well. And then I went for, oops, the image is not in there exactly, but I went for PLK-SR, the tiny version, because you can't really much see it here, but SR Former Lite, PLK-SR, performed around the same as SR Former Lite, but is way faster. So it's a pretty good network. And the tiny one is even faster. I did a speed test for training because I wanted these tests to not take forever, because there is a lot I want to test. And so I wanted a fast network, and PLK-SR Tiny was pretty fast here, while also being one that's, that has a paper to it that where you can read the details about it and stuff. And PLKs tiny, while being pretty fast, actually had higher matrix also than span. So that's a pretty good sign. So I wanted to try out PLKs tiny and use that one for those tests. You can see a training config here. That's the base model, or the baseline. I want to use just the PLKs tiny model, only trained on DF2K, all the tiles. And you can see, this is still ongoing, of course. I'm still doing all the tests. Like I said, would be cool if I can do all the tests and then, see some things and then write something about it, maybe a little report or something. But here you can see the training, the DF2K PLSR Tiny as a baseline model in, this light blue, trained to around 500K for 12 hours or something. Then I, did complexity filtering with 0.5 and started training. Then I did blockiness and cut off anything above or at 2 and started training. And then I did the cualign scoring or filtering at 4, and then I started training. And this is the PSNR. And we can see some things here, pretty interesting. So complexity, as you can see, started learning way faster. So it learned things way faster with more complex images. Then blockiness, for example, if I filtered with blockiness, it had around the same performance as the baseline model. Interesting enough, with PSNR, it was always a little bit below the baseline, but the longer iterations it went a little bit above it. And so the paper showed that, if you have bad blockiness in your data set, the longer you train, the more detrimental it can become for your data set. So I get the same here with this small test. But that it doesn't really improve the quality, it improves, or in at least in this case, just with that value for this data set. Yeah, so interesting here also for a cualign filtered here gives worse scores for PSNR, but that also shows again how important the metric is that's being used. PSNR is a pretty old one. You can see it here again, and then here. This lower is better, and yeah, I like this here. And you can see here it's the other way around. So here cualign 4 actually gives the best performance. So of course, what I need to do is more tests, but I also would need to, run inference on all of those models, then save all the validation output, and then visually spec all the validation output to see for myself, is it better or is it worse? Then you can see complexity also learned faster, but also here in the test in comparison to PSNR here, well, at least at the state of 70,000 iterations, would of course still need more training, still ongoing, like I said, but here it actually performed better than the baseline. Here it's around baseline level, here it performs better than the baseline. So just to show also the metric that you use, how much of an influence that has to look at, visual examples, which can of course also be tested with more metrics. And then there's still more tests I want to do, right? I want to do now a combined version of the filtering methods. How does that one score in comparison to the others? Then I want to, with the complexity 0.5, what is the influence if I train one with complexity 0.4 and one with complexity 0.6? Does it increase from 0.5 to 0.6? Can I, with complexity scoring, actually, get better performance than this QLine 4 scored? What happens if I combine them? So a lot of training I still want to do, a lot of way more models training, and see all of those differences. And once I see that, you can see here, for example, it scores a little bit better, but the differences are pretty small. So another test then would be, what if I increase patch size? Will the differences become way bigger? Will the model profit more from a curation process? And then a bigger network, for example, if I use the normal PLKSR option already, does a bigger network with bigger patch sizes, profit even more from such a curation, process or not? So yeah, so there's still a lot of more testing I want to do and training. That's where I'm at. I just wanted to show that. Pretty interesting stuff, fascinating to me. I hope for you as well. And yeah, thank you for watching my video.